Okay, so I think we'll get started. So I didn't have a whole lot of questions to go through today. I mostly wanted to just work through a couple and then, or actually I guess two, and then if anybody had any questions regarding the IAS emulator. I know it's, like phase 2 is already due, but I assume there's going to be a phase 3. So if anybody had any questions regarding, like, what you've done so far on that, and then maybe some other questions from the book or on lecture, just if anybody has them. So yeah, let's just get started. So, let's ignore B on this one, just because I think it was a little convoluted. But they want us to consider a disk that rotates at 3600 RPM. The seek time to move the head between adjacent tracks is 2 milliseconds. There are 32 sectors per track, which are stored in linear order, 0 through 31. The head sees the sectors in ascending order, and assume the read-write head is positioned at the start of sector 1 on track 8. There is a main memory buffer large enough... Oh yeah, right, make sure to post in chat for attendance. Memory buffer large enough to hold an entire track. Data is transferred between disk locations by reading from the source track into the main memory buffer and then writing the data. So it has a buffer to store things in, I guess, is one key point of this. So, first question, and again, we'll just ignore B, because I think it was way too complicated. Even this one, I think, was a little out there. But I guess it makes sense. So, how long will it take to transfer Sector 1 on Track 8 to Sector 1 on Track 9? So, just as a reminder, if we have a disk that looks better than that, then there are tracks and there are sectors. So tracks are like these concentric circles, and then the sectors are like these areas. So this whole outer ring right here would be like track 0, and then this one would be track 1, and then that one would be track 2 in the middle there. And then this might be like sector 0, 1, 2, 3, 4, 5, etc. So the sectors are just on each individual track. So we want to go from one track to another track, and then basically copy to the same sector. So we're going to basically start somewhere like here, and then the disk is rotating around, right, and then we need to copy it over there. So we first maybe want to consider the fact that we need to rotate all the way around in order to get from here to there, because by the time I've read this whole thing into the buffer, I'm already going to have been past this part right here, this sector, on the next track down. So I won't be able to immediately copy it over because the disk will be spinning too fast. So let's first consider how long does it take for the whole disk to spin around the circle. So if it's 3600 revolutions per minute, and we want to know the time that it takes for it to do a single revolution, would be kind of helpful, and potentially even just through a sector. So we probably want it not to be in minutes, but rather milliseconds, because that's the amount of time that they use for this here, so it'd be good to have it consistent. So first, let's try to get this flipped. So that'll be 1 minute for every 3600 revolutions. And the reason I'm doing that is so that we have time on the top and revolution on the bottom. That way we have time per revolution. And then we could say something like, well, that would be 60 seconds per 3600 revs. And then that would be... So if we want to convert to milliseconds, right, 60 milliseconds would be 60 times 1000. Milliseconds per 3600 revs. Everything seem clear with that so far? Hopefully. I know I could have done the dimensional analysis or whatever and like multiplied all the fractions, but I hope this one's straightforward enough. Okay, cool. So if we just divide this really quick, that 0 cancels there. 36 divided by 6 is 6, and then we can cancel one more 0 there, and then we get 100 over 6, which would be 50 over 3. Right, and so that's about, actually I guess it would be 100 over 6. So it's about 16, right? 16.6 repeated, I think. So that means that it takes 16 point, let's just say 7 because it'll be 6 repeated, milliseconds for one revolution around the whole disk. Now, what the book does here, which is okay, I mean, it's fair enough, is they say, well, and you know, maybe, let's just still go over it, because maybe it'll come up on the test. It's 16.7 milliseconds per one revolution. We probably want to figure out how long it takes to just move from one sector to the next. So what do I have to do to figure out how long it takes for it to go through a single sector on a track? So consider that, yeah, okay, awesome, right? Divide by sectors per track, yeah. So everybody's saying that. Yeah, so we want to divide by the number of sectors per track, because if this is the time that it takes to revolve basically one track worth of distance, then we know it'll be divided by 32 or divided by the number of sectors per track, which is 32 sectors. So that's about 1/2, a little bit bigger, I guess. I have the exact number in the answer key. Let's find out. 7.7, 0.52, they say. So 0.52 milliseconds per sector. Okay. So again, we'll avoid this if anything. Actually, no, I think we do need it for one calculation here when we think about it. But yeah, just know that you can just divide that to get it. So then let's consider what's actually happening here. We're going, again, we need to start at this one, read it into the buffer, and then we have to do the revolution around the whole disk. And meanwhile, we need to move the read head, which is on the outer track right now. So the read head is aligned here, and we need to move it one track in so that it can move, I guess it's a read-write head, so that it can write to this part right here. So what we could do is we could like read from this, revolve all the way around, and then transfer the head down, right? That would be fine, but we can kind of kill two birds with one stone, or I guess accomplish something else while we're doing this in parallel. So we read this, and then we kind of just wasting time waiting for the read head or read-write head to like rotate around this whole thing or go with the disk, right? So what we can do is actually move it from this track to the next track in while it's spinning around in a circle, because it needs to go around the whole thing. So rather than say, oh, it's going to be 16.7 plus the 2 milliseconds that it takes to move the read-write head from this track to that track, and then the last 52 milliseconds to actually write the data back to this sector 1. We can actually ignore this 2 milliseconds, and the reason being is that we can move, like I said earlier, move the read-write head from this outer track to the inner track while it's spinning around to get back to sector 1 again. So the total time would only be the 16.7 it takes to rotate around the whole time. That includes the read time of this because that's part of the whole first revolution. And then the extra time it takes to go around this sector. So basically the path of it is something like this. That's not drawn very well, but it goes around in one full circle, and then it kind of goes just one more sector past. So let's say that's one sector. So if we add this together, this would be, what, 17.22 milliseconds that it takes for that to happen? Does that make sense? Are any questions on that at all? Cool. And some of these do seem to get convoluted. Just consider scenarios where you're able to move the read-write head from one track to the next while you're spinning, because there might be some overlap in this case. The next one had a bunch of cases, I think, where it wasn't, or you had to like move it, but the time didn't line up perfectly, so you had to like do a bunch of like halfway calculations with the sectors, and I don't know, it just seemed a little too convoluted. I didn't want to go all the way through it, but at least wanted to get over the basics. Okay. So I only really have one other one, and then we'll just talk about whatever. This one was about paging, so this is 9.6. So suppose the page table for the process currently executing on the processor looks like the following. All numbers are in decimal, and everything is started from 0, and all memory addresses are byte addressable, and the page size is 1024 bits, or bytes. Okay. So really, we can ignore all this stuff in the middle in this page table. The important thing is this column over here and this column over here. These are the two important ones. The other stuff is just for keeping maybe some metadata on the pages. So describe exactly how, in general, a virtual address generated by the CPU is translated into a physical main memory address. Okay. So I guess the first question I have is, everybody clear on what paging is, or do you want me to talk about that a little bit? Yeah, talk about it? Okay, I can do that. So let me open a new page here really quick. So let's say you have RAM. And RAM is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's just do 10. It's 10 memory units, whatever this is. The amount doesn't really matter. There's some arbitrary memory unit that everything happens to fall nicely into. And then we have a hard drive over here, HDD, and on the hard drive you have Google Chrome, which is 4 memory blocks. That's how much memory it needs to run. And then I have WebEx, which we're writing right now. And that's maybe 3. And then we'll say Discord also takes something like 3. I have to be careful about where I load all this stuff into. And then, I don't know. We'll have something else. We'll just say like Steam. Whatever. And that takes way less than Steam probably actually takes. We'll just say it takes 2. I just want a small one. So I want to be able to fit all of these in RAM. So let's see. What order should I do this in? If I do WebEx, and then Steam, and then Discord. Yeah, that should be fine. So I open up WebEx first. And then, so let's just say that immediately gets loaded into the beginning of memory. So it takes 3 blocks, right? So I'm going to load it here, here, and here. And WebEx is now running. And it now has all the space it needs to load all of its program data, instructions data for variables, all that stuff. Cool. And then now I say I want to open up Steam. Okay, so I open up Steam. Again, that takes 2 memory blocks, so I just load that immediately into RAM there. And now it's running. I'll just write the letter just in case anybody's colorblind. And then, yeah. So next I run Discord. And that takes 3 memory blocks. So I go here, and here, and here, and all those get loaded into RAM, and it can run. So now I decide I don't want to run Steam anymore. So if I try to run Chrome now, right, obviously it's not going to have enough RAM to run, and so you're going to get some sort of reply from the operating system saying that you can't load it in. And it shouldn't be able to run because all this memory is allocated for other programs, so, you know, this space we don't need. But I close Steam. Close Steam. And so now Steam's memory is going to get deallocated. We don't need it anymore, right? Out of memory. Okay. Now I want to load Chrome. Can I do it? At least with the way we have it set up right now. Well, no, I can't. Because even though I have the correct amount of space, right? There's 4 blocks here, 4 blocks there. There are 4 spaces, but they're not all next to each other. So if I try to like fit this block into this space right there, it doesn't work. And if I fit it right there, it doesn't work either. So the solution to that, and so I guess one solution, I think somebody said move over. We could take all of this space for like Discord and then move it down to, I guess. But there's a couple problems with that. One, if I have a really big memory space, then figuring out the optimal way to arrange those things is going to be really, really difficult. So obviously for this example, it's not too hard. We just move it down 2 units. But figuring it out is hard. And then on top of that, we have to actually physically pick that memory up and copy it down 2 memory blocks lower, right? Which means that, and in this case, there's not even really enough space to like store a buffer or anything like that unless we build it into hardware. So this would probably need to get written back to disk, halt the execution of the program entirely, because we're going to be modifying the data, and then move it down here, and that's just going to take forever. So that's a lot of time. So somebody said yes, which they might be a little bit ahead of me here. So yes, there's enough space, and the way we go about fixing this is with paging. So with paging, what we do is we take each of these blocks. They're fixed size. It's determined at run, or not at runtime. When you start up your operating system, it will have some sort of variable that you can actually modify in your system settings, where you determine what these blocks are that are individually going to be thrown into RAM, and those are called pages. And so it's a way that we can actually stratify. So if I page this now, I would throw a page there, page there, page there, page there. And then now I can fit Chrome. So paging is a helpful way to actually do that. Now the problem with paging, which is not a huge deal, it's worth the fact that we can fit more stuff in there, is that if this is stratified like this, it's split up, we need to figure out where it actually came from, and then we also kind of don't want the program to be able to leave this region. And and so we need to kind of limit it, and then we have like multiple regions. And then on top of that, there's something else I was thinking of. Now I'm forgetting. Something with page faults, maybe. Oh, yes, yeah. So we had a temporal locality, right? It was something we talked about a few weeks ago. So now if Chrome, for whatever reason, needs to access variable x, which is at the very, very bottom of this page, and then needs to access variable y at the bottom of, or the top of this page, then we kind of lose that. Did I say temporal locality? I meant spatial locality. We kind of lose that advantage of spatial locality because now these aren't actually next to each other. They're paged apart. So that's called a page fault, if you've ever seen that term before. Which basically just means we have to load the page into memory. Or I guess the page fault would be like the individual splits, but we kind of have that difference there. Does that make sense so far on what pages are? There's just a way to split that data up so that we can fit more stuff in there. So we'll go back really quick to this one here. So the program can be split. Yep. And so what we're going to discuss here, I guess, in a second, is the extra overhead we have to go through to make sure this happens. So we end up getting RAID. Well, RAID is a method for storing things in secondary memory, like a hard drive or a solid state. This is more for loading things from memory. And RAID, depending on the number, like varies quite a bit. So RAID is like a way to keep backup for data, I guess I would say. In most cases. That's not even necessarily true for like RAID 0. But this is more for loading things, whereas RAID is for storing things and usually keeping redundancy checks, or not checks, but redundancy in your data so that if one drive fails, you have more backup data. So paging is a way to divide main memory for programs. Windows does it, yeah, but every operating system should have it in some regard. OS X, Linux. I guess that's really all we'll stick with. But yeah, pretty much every operating system has some form of paging. And they should. The overhead from it is not that bad. So you'll see here in a second that it takes a little bit of extra time to actually do it. But it's kind of worth it because then we can just load more stuff. So describe exactly how in general a virtual address generated by the CPU is translated into a physical main memory address. So if we go back to that example really quick, there's a distinction between virtual and physical addresses. So physical address, and again, let's just say, for simplicity's sake, that it's something like this. I don't even need to put the hex. Obviously the address is going to be way longer in reality. But let's just say it looks something like that. As far as the program is concerned, so these are the actual physical addresses on RAM. This is the bit that's right next to it. This here, 2, 3, is the virtual address that the program sees. So Chrome thinks this block is 0, but in reality it's 4. It thinks this one's 1, but in reality it's 5. This one's 2, and in reality it's 9. So there's a distinction between the physical actual address that it's at in RAM and the virtual address that the program can see that the page table is going to keep track of. So that's just what that means. So basically we keep the virtual page number, which is the page as far as the program is, and then we keep in the table, which is the operating system is responsible for this. It's not physically built into the hardware. It keeps track of where it actually is in memory, if it's in memory. So you'll notice here these ones are just null, which means that it's not actually loaded into memory right now. We do that just because we might not need actual parts of a program at every given moment. So you might only have, let's just say, I'm way oversimplifying it, but let's just say you have like line 100 of your code to line 200 of your code. Maybe that's only loaded into memory, and 0 through 99 got swapped out by the operating system, and you probably don't need to go back to it anyways, because if you're in like your main in C++, you're not going to jump back up. Obviously that's different when we talk about function calls and stuff like that, but yeah, so it gets swapped out. That's the other nice thing. We don't have to have the entire program load it in all at once. We can just bring in certain pages when we need them. So it's almost similar to a cache in terms of like loading things in and out, but not for speed purposes, and also a little bit different. So if we want to describe exactly in general how a virtual address is generated by the CPU, is translated into a physical main memory address. So let's say here that I wanted to, I could even do this 1052. Yeah, let's do it with an example. So let's say I want to convert 1052 from a virtual into a physical. So I have RAM. Actually, I guess this is backwards. This is physical into virtual. Yeah, let's talk about the other one really quick. So if I wanted to go from a virtual to a physical, all of my virtual addresses are going to correspond to a page number. So 0 through 1024 in the virtual memory. 0 through 1024, that's going to be virtual page 1, or 0, we start counting at 0. And then 1025 through 2048, those are going to be, wait, I'm counting wrong. This would be 1024, this would be 1023, right? 1024 to 2047, that'd be virtual page 1. And then if I had 2048 to 3071, I think, virtual page 2. So like these blocks, since they're 1024, these pages, that's what the virtual page that the actual program sees. It's just going to see them in contiguous order. So the first 1024 bytes, that's the first page. The second 1024 bytes, that's the second page, and then, so on and so forth. So I would need to first figure out which virtual page it's on. So if I was to just take a arbitrary virtual address, can anybody think of one single operation I can do to figure out what page it's on? Virtual page it's on. What do all numbers in this category on the left do to map into these numbers on the right? There's one math operation. Not modulus. We'll use that in a second. Because if I consider 0, 1, 2, 3, 4 are all in here, but if I modulus that by something, they're all going to be like 0, 1, 2, 3, 4, but they're all on page 0 instead. Although we'll use that in a second because that's kind of like the leftover part, right? Modulus is for a remainder. So if it's not modulus, and we're going to use that, then yeah, exactly. We're going to do the divide, right? 0, any number from 0 to 1023 divided by 1024, which is our page size, is 0. 1024 to 2047, any of those divided by 1024 is 1. 2048 onwards, 2. Does that make sense? This one's division. And then if we wanted to get the offset, that's modulus, which is actually similar to the cache as well. So the first thing we would do is we would take the address. So I guess if I do A over here, I wrote A twice. Right, A over here. We would take the address, divide by the page size. Let's put S. And then now we can use that to look in the page table. Sorry, I'm writing kind of small there. So if I had, let's say, 1052 as a virtual address, I would look in the page table. That's on page 1 because 1052 divided by 1024 with integer arithmetic is 1. And then I would say, okay, well, that's at page frame number 7 in actual RAM. So I would then kind of go backwards, right? I would multiply the physical, and then when they say page frame, that just refers to those like segments that I was drawing earlier. So multiply physical page by the page size. And the reason is, if this is on the 7th page, then we know it's 7 times 1024 bits, or bytes, is the start of that page. Because each of them are equal size, right? So we can just multiply to get to there. And then, all we have to do is, so that if that gets us to the starting position of that block, again, consider if I was in page 7, then this address right here is 7 times 1024. And then I have, like, you know, a bunch of different variables here, enough to take up 1024 bytes. I think it was bytes, right? Not bits. Yeah. So 1024 words of some kind, or no, I guess bytes. No, that's right. So if I want to get to that individual byte, then I just need to figure out what the offset is. And again, that would just be whatever comes after the 1024 part, the modulus. So we would add the address mod page size. And you know, you could probably do that a little bit faster just because we know the last bytes are going to be the modulus anyways, so we could probably just truncate the top bytes and then AND them in with like a XOR would be the correct operation. XOR them in with like just the first how many ever bytes, and that would save you some time. But if we were just speaking on like a, oh, I'm going to emulate it kind of point of view, that's the math behind it. Does it generally make sense to everybody, or any questions on that method to go backwards? We're basically just going to do the same thing for these ones here, just the other way around. Yeah. Okay, fair enough. And again, if you have questions, just stop me at any time. Okay, so now let's go the other way. Let's say I have a physical address and I need to map it to a page for a program. And we do not try to handle page faults, if any. Oh, I'm sorry, I was reading this backwards. No, this is exactly what we're going to do. We're going to turn the virtual address into a physical address. Actually, that makes sense because we kind of need to know information about the program to do the other way around. Yeah. So let's start with 1052. I'm going to probably erase this. I don't think I'll need it. So first off, what's the virtual page of 1052? For this specific example. 1, right? Because if we look at this, we want to take the address divided by the page size, and 1052 divided by 1024 is 1. And just so we keep track of it, 1052 modulus 1024 is 28, I think. 8 would be 32 plus that. Yeah, it should be 28. And correct me if I'm wrong. So what we have to do is that's the virtual page, right? Since this is a virtual address, that's the virtual page. We go into the virtual page table, or we go into the page table. We look for the virtual page that it belongs to, and that's right there. So we know the actual page that it belongs to is 7. So what am I going to do with that 7 if I want to go into actual RAM now? What's the starting address of the page 7? Or at least how do I find it? You don't have to give me the exact number. I'd have to think it through a little bit. Yeah, I think I have it. So that would be exactly this, right? 7168? Yeah. 7 times 1024. Actually, if I was to draw that out, the reason is we know we're going to have page 0, page 1, page 2, page 3, ... until we get to page 7. So, similar to this, because the pages are the exact same size, this goes from 0 to 1023, this goes from 1024 to 2047, 2048, 37.1. So each of these are 1024. Right? And then, yeah, exactly. And we're going to add that 28 to it. Yep. So just to be clear, each of these is 1024, so we'd have 7 groups before this because it'd be 0 through 6 before we get to block 7, so we need to do 7 times 1024 to get to the top of that block, which is 7168. And then, like somebody was saying, we are going to then add the address mod page 5, which we figured out earlier is 28. So we would take 7168 plus 28, which is 76 plus 20, 96, I think. That's for B1. Is that clear? And we'll maybe do at least one more. Makes sense? Okay, let's just do one more really quick, and I won't do a whole lot. I'll just let you guys answer it. So I want to figure out 22.1. So what's the virtual page for that one? 2? Yep. Right. Because 22.1 divided by 1024 is 2. And then, as an aside, what is the offset? Let's see. $173? That sounds right. 48. 48 plus 173. Man, I'm struggling with math right now. 48 plus 3 is 51 plus that. Yeah. Yeah, and everybody's saying, yeah, should be 173. Sorry, bits. I'm having some trouble with the mental math. Alright, so we know the offset is 173, and we know the virtual page is 2. So then what's going to be the physical? Actually, I guess that's a bit of a trick question. We go into virtual page. We check 2, because that's our virtual page number. We have a page fault, because there's no page there. We've got to the fault of a page, which is just, the split. And it's not in memory. So we just let the operating system handle it. It does whatever it needs to do to move that in from secondary memory to main memory. But I guess the question here was just asking for the actual physical address, and there's none because it's not actually in RAM right now. Okay, so that one's done. And then last one, which I don't have space for. We'll just try to do it in our heads. 5499. What is the virtual page for that one, first off? Should be 5, yeah. Because 1024 times 5 is 5,120. And that seems to be a little bit bigger than that, yeah. So 5 seems good. And then, so what's the page for that one? In reality, it will be at 0. So we know it's up here at the very start of RAM. And then what's the actual address going to be now? That one shouldn't be that hard to figure out. Yeah, okay, awesome. Everybody's saying, yep, 379. Since 5499 mod 1024 is 379 because that's, this plus 379 equals that. Cool. And then so that would be 0 at the top, and then plus 379. It's somewhere around there. Does that all seem good, or does anybody want to do more examples of that? Paging, I think, is kind of important because you'll do this in operating systems as well. Okay, cool. Everybody seems to be good. And again, if you have questions, stop me. Don't be afraid to ask. Okay, so those were really the only examples I wanted to go through today. We still got 50 minutes. So I just wanted to ask, there's a couple things we could go through. So we could either do some more examples of other stuff. I can either look in the book or just try to explain it. Or we could go over the IAS simulator. So what I was thinking of is either IAS or we go over data representation, which I think everybody did in 218, so I was kind of iffy on doing it, which was, how do I represent an integer, 2's complement, IEEE floating point. But I mean, maybe people want to review that just to remember it. And then Booth's algorithm was the other one I was thinking of. Or we could talk about RAID. I mean, I don't know a whole lot about RAID, but I can at least discuss what each one is and kind of like the important ones. Think about the final phase for the project. Fair. I'll wait for more responses. So there's the problem of I don't know what the final phase is either. So just consider that. I don't actually know what it is. But everybody seems to be saying IAS. Okay. Yeah, that's almost overwhelming for me personally. You got questions? IAS. Okay, that's almost like overwhelmingly IAS, which I guess is fair. It's kind of a hard program. And do one example of Booth's algorithm? Yeah. Maybe let's do Booth's algorithm really quick. I'll just do a quick example of it, and then we'll go through maybe some structure and some question on that. Booth's algorithm was a little confusing to me when I took this class. So let's just really quick. I'm not going to go into a whole lot of depth here. Let's say I want to do 4 times 7, which is obviously 28. And so I want to consider these in binary. So 4 is 1, 0, 0, 0. And I'm going to multiply that by 7, which is 0, 1, 1, 1. So 0, 1, 0, 0. And then we'll say b, which is the thing that we're multiplying by, is 0, 1, 1, 1. So with Booth's algorithm, what you should do is calculate the negative version of whatever you're multiplying by. So I'm just going to do 4 as the first multiplicand and 7 as the second. But realistically, the order doesn't matter because it's associative. So does anybody know how to figure out the negative version of 7 in 2's complement? Invert then plus 1. Yep, okay, so everybody seems to be saying that. So just as an aside, we take whatever the value is, we invert all the bits, and then we add 1. So invert, and we add 1, and then that's 1, 0, 0, 1. 0, 1. Okay. So we're just going to note these two down here. So for Booth's algorithm, we need a register that is double the size of the biggest thing we're multiplying by. So in this case, they're both 4 bits, so our register is going to be 8 bits. So what I'm going to do is I'm going to make an 8-bit register, 0, 0, and I'm going to populate the least significant 4 bits, or whatever, how many bits this is, with the number that I want to multiply. So in this case, that, and then I'm going to also throw a like a carry out or a fall off bit, and we're going to initialize that to 0. Okay. So what I need to do with boost algorithm, and it's a little strange, if I'm going to be honest, I don't really understand the shift part, but I can at least explain how it works, or like what we do. We want to compare at any given point the last bit of our word and the bit in the carryout. So if they match, we do nothing. If it is 0, 1, then we are going to add B to the most significant bits. And if it's 1, 0, we're going to subtract B, which is why we calculated this part, the negative B. We're just going to add the negative because that makes more sense to do in the context of the computer, to the most significant bit. Okay. And we're only going to do this until everything in our original thing that we're multiplying by, so these 4 bytes, has moved out of the register completely. So once this 0 leaves, then we're done. Okay. So the first thing we're going to do is we're going to look at, and maybe I should put a split here. There's like a bit of a split. Okay. So I consult that whole match part. Do they match? Yes. So we're going to do nothing. And then I want to shift. So 0, 0, 0, 0, 0, 0, 1, 0, and then this 0 is now going to end up in the carry register. Maybe we'll do this here. Okay. And again, we have 0, 0. These match, so we do nothing. So let me just write down what I did. So I shift. And then again, I do nothing because they're both zeros. 0, 0, 0, 1, 0. So this 0 moves into the carry register. And this 1 moves over here now. And I shift. An important thing to note about the shift is that whenever you do it, you need to... so I'm doing it 0 here, which is kind of, what you'd expect it to be, right? We want to make sure that it's the same as whatever the most significant bit is, and the reason is if we're doing multiplication, whenever we shift, we want to make sure that the most significant bit, which is just the sign, 1 or -1, is the same. So that's why we keep it. Okay, so now I get that the 2 bits on the end, that's 1, 0. So what I'm going to do is I'm going to subtract by B. Or in other words, I'm going to add -B to the most significant bits. So I'm going to take -B that we had here, which is 1, 0, 0, 1, and I'm going to add it to the most significant bits. So we get 1, 0, 0, 1, 0, 0, 0, 1, 0. And this is before I'm shifting. So I subtracted B because of the fact that that's what that says. Okay, and then now we did the operation. So before it was do nothing, but we've done the operation now. So we will again continue to shift until we've reached 4 shifts and the whole word is outside of the register. So here you'll see that instead of shifting a 0, and I'm going to shift a 1 because this one was a 1 originally. So it's a 1 now, so that we preserve the sign. So 0, 0, 1, 0, 0, 0, 1. Okay, and right now these are the only 2 that are left over from our original 4 that we had. And again, we want to compare these 2. Okay, so in this case, we get 0, 1, which is add B to the most significant bits. So kind of like last time where we added in 1001, we're going to add in positive b this time, which is 0, 1, 1, 1. And then we're going to get 1, 1, 1, 1. Where did I get this one from? Oh, from out there. 1, 0, 0, 0, 1. Okay. So here I added b. And then, again, we did the operation, in this case, adding. So we're going to shift again. And again, I want to keep the MSB. 1, 1, 1, 0, 0, 0. And now we should be done because we shifted 1, 2, 3, 4 times. The only bit that's left over from our first word was this one here. And it's in the carryout, so really we've moved the thing out. So let's just double check that this is correct. So that's 1, 2, 4, 8. So this is 4 plus 8 plus 16 plus 32. This seems way too big. I clearly did something wrong. Oh, wait, this is 2 complement, though. Well, that's 28. I should get a 1 up at the front. Oh, that's a 0. That's a 0. 1 plus 1 is 0, right? So that's a 0 there. Yeah, I'm sorry. This is 1 plus 1 is 0, and then carry the 1. 1 plus 1 is 0. So this would be 0, 0, 0. Is that clear what I did wrong? Just really quick. Hopefully everybody sees that, but if you don't get what I did wrong, just let me know and I can explain it. So our actual answer is 1, 2 aren't there, so this would be bit 4, 8, 16, so 4 plus 8 plus 16 is 28, which is what we expect. Yeah, so that's right. Any questions on that before I move on to IAS? I know that was a really quick version of it. I just wanted to do an example because I know it's all over the place sometimes. Okay, one all good. Okay, fair enough. If nobody has any questions, then I guess we'll just look at IES really quick. So, was there anything anybody wanted to talk about in particular in regards to IAS? Caching, the interrupt system, just generally how it works. Maybe a more organized way of doing it. Hamming code? Yeah, that one's a little tricky. What do you think will be in phase 3? Let's see, what have you guys been doing in class? It's been paging. That doesn't make any sense. Probably wouldn't be doing paging. Already finished hamming code. I think so. I know the final phase is the only one I'm grading. I don't know if all the individual phases are worth 200. I think that makes sense to have it just be worth 200 at the end, because otherwise that's a lot of points. That'd be like 600. The 200 for participation? I'm not too sure. I don't think so. I think those ones on the website are just to make sure that you're actually making progress on it. First 2 phases. Yeah, I don't really have a guess. I'm not even sure what's coming up in the book. I'm forgetting. I did interrupts. Does that mean we don't fully complete phase 2? We could fix it for 3 and get full points. Yeah, I believe so. You're just trying to make sure that everything works, I guess, in the long run. Are you testing the project based on the IES files? I am probably going to do that unless I know that you put in your documentation that you use something else. But that would make it easier for me to test, and I think it would probably also make it easier for you to debug if you did the IES files. What kind of files? So I want whatever your source is, the py or the .cpp, whatever language you wrote it in, and then ideally some kind of documentation that just tells me how to use it, because some people might read from a file and some people might not, and you might have different command line arguments. So I would kind of like it if you wrote like a short PDF or a Word document or something like that, or even like a text file. I don't really care. Just something to clarify. I mean, I can look through the comments in the source code, but I don't know. That's a little bit hard to do. Okay, so I'm gonna maybe. Well, so somebody said Hamming code. That's the only thing I've seen. Is there anything else we want to go over? I can try to write some code for the Hamming code. Yeah, no, that's I guess what I'm saying. Let me find some stuff really quick. 219. I hope I didn't delete that. Alright. I don't see it. I might have accidentally deleted it. Oh well, that's okay. Yeah, maybe I'll... Oh wait, I don't think I'll have time to go into detail about Phase 3, because again, I don't know what it actually is. And we don't have discussion until the day before the final. Oh, we can do the double error detection too. Yeah, let's try to get as much of that done in the next 30 minutes as we can. So just Phase 2 in case anybody needs to correct it. GA 218. Okay. I don't really think I need to write these, but that's fine. Okay. Okay, so for the Hamming error correction, so obviously from the first phase we had fetch, execute the code. Also, is the code easy to see, or should I maybe zoom in a little bit more? It's visible? I can see it? Okay. I don't even think this lets me zoom in anyways. Okay. Alright, fair enough. Kind of hard for me to see. Maybe I'll... Yeah, it's okay. I'll zoom in a little bit. I think it's probably a bit small. It's just a question of... How do I zoom in? Full screen? Zen mode. Is that a little bit better? Oh, Control Plus. I don't know if that's too far zoomed in. If that's better, then hopefully that's okay. So you want to fetch, execute, decode, assuming you've written all these functions somewhere. Then what we wanted to do was handle interrupt, right? And again, we're assuming we have... So I know I told some people to do this now. If I want to go for more of an object-oriented approach, and also to make things maybe a little bit easier, I can make a struct for the CPU that has the accumulator, the current instruction in the register, and then, I don't know, that's probably fine. I think that's all we really need, right? Maybe an MQ if you really wanted an MQ. Okay. Do that. So I have some function that handles the interrupt. Actually, let's make that a global so I don't have to pass it in. Handle interrupt. That's 4. Okay. So there's 2 cases that we had to worry about, right? Which was the store IO and the load IO, and they're both going to do pretty much the same thing. So let me go get the opcode enums. So in all these preprocessor directives using namespace standard. Okay. So yeah, then we also had opcode and operand. Again, I'll just make them globals for the sake of making things easy. So what we wanted to do is we wanted to check bool is interrupt. So if we encountered either load IO or store IO in the... Oh, I put this in the wrong order. Fetch, decode, execute. So if I encounter either load IO or store IO in the execute function, I want it to set the interrupt flag here to be true so that I know that there's an interrupt. And then also, let's just say we have an IO device as well. Okay, we'll just do that as an int. So remember that the IO device is just an 8-bit integer. It's one single memory space. So that's why you'll notice in the code, because I got a lot of questions about it, load IO and store IO, I just put zeros for the operand. I could put anything there. It doesn't really matter. We're just saying it's one memory space. So if I put 0, if I put 4000, it doesn't make a difference. We're just going to ignore it. We're going to throw out the operand. Okay. So I am going to then say, okay, if there is an interrupt, so this is pretty much just the same code from last week. If there is an interrupt, then do something. So if there's not an interrupt, we'll just do nothing. We'll return. Else handle interrupt. And then obviously I want to do something like a switch statement or some if blocks, and then just say switch opcode. And we say case store IO break case load IO break. Okay, so hopefully everybody has at least this much. So from when I'm doing store IO, I want to do a couple things. So I'm going to have some sort of data in the accumulator. So I'm going to move from the accumulator to the IO device. And I'm going to transfer an entire Hamming code over. So what I suggested to a lot of people was to return a Boolean array that contains the Hamming code. So generate Hamming code from value, let's just say int value. So this takes whatever the contents of the accumulator is, and it's going to turn it into a Hamming code. So bool, God, how do I do this in C++? That's elegant. I mean, we can just allocate space. I might be doing something extra here. I don't remember how C++ does this, but bool, let's say Hamming, and that. I don't think I'm allowed to leave this without a value in C++, so let's just say this is fine. So Hamming equals generate Hamming code from value CPU.ac. Okay. Just to make this easier for the what's it called? The IDE. And then we'll generate Hamming code from received code. So we're going to need two, really. Or at least I would suggest doing two. So we have one for when we actually are going to send the value, and then one when we receive it on the receiver side. And again, I'm hoping all this is right for C++ syntax. So yeah, first thing we need to do is we need to, before we're sending it to the I/O device, we need to generate the I/O. Generate the Hamming code for the sender. So whenever you're doing a Hamming code in practice, it should be done before you're storing something or before you're sending something, either in this case to a drive, or over a network. You might get some problems with not receiving exactly the correct thing just because of interference. So we need to generate it on the sender side, and then we'll generate a second one on the receiver side. So I recommend doing it as a Boolean array, where every single position is a bit 1 or 0. So true for 1, false for 0. That way we can do the XOR stuff pretty easily. So the first question I have, and I'm pretty sure everybody can figure it out just from looking at the code, if the values of things that I'm sending are 8 bits, what is the size of the Hamming code that I need to generate? $12 bits, right? Because we have 8, the log base 2 of 8 is 3, and then we need an extra bit for 0. So we need 4 extra bits for check bits, and then we can add that to the 8. So that'd be 12 in total. So I'm just going to make a Boolean array. Hamming code 12. Okay. So I need to first populate all of the positions with the data bits, and then I'll calculate the check bits. I think that's the easiest way to go about doing it. So first, populate the code with data bits. Okay. So I need to copy position 1 to 3, position 2 to 5, all that kind of stuff, right? So let's see. I think I said that right. So I'm sure there's a bunch of different ways you could do this. The first way that comes to my mind when I just think of it right now, so for int I equals 0, let's say int Hamming index equals 0. So we'll do this one that writes to the Hamming code. Actually, we can kind of shortcut this. We know it's going to start at position 2. Okay, just because indices are 1 less, and that Hamming code version that we did had check bit 1, check bit 2, and then data bit 3, and then so data bit 3 would be -1, 2 in our actual thing. And then I'll have I, which is just counting through the positions in that. Actually, maybe the better name for this is data. No, that's fine. That's right. And then we'll say int data index 0. So I'll just use I. Hamming index will be the index into the Hamming code array, and then I will be the index looking at the data values. And if anybody needs to see this drawn out, I can draw it out too. So we want to go from I0 to I less than 8, I plus plus. Again, I is the index pointing to elements in the data value. Okay. So what we should do is, and again, there's probably a way more efficient way to do this. We should probably figure out where exactly we need to put something into the Hamming array. So I would say while that's a good way to do this. We need to check it against a power of 2. Using math.pow is a bad idea. And if anybody has any alternative solution to this, by all means, stop me. So I'm thinking just keep an array of all the values we need. That's bad. That's not very abstract. Did it manually? That is an option too. I and I minus 1, like with a bitwise operator. I and I minus 1. It's either going to be 0 or 1, right? No, I'm wrong. Because power of 2 is going to have 1 and then entirely 0. So if I would have like 1, 1, 1, 1, 1, ANDed with that is 0. Right, and that's going to be true for all of them because it's going to go from 1 to that. And then nothing else is going to flip bits exactly. Yeah, so if we check it versus I minus 1 bitwise and it, and then check if that's equal to 0, that should mean that it's a power of 2. I think you're right. That sounds like a good way to do it. That's actually way better than what I was planning on doing, so thank you for that. So while Hamming index, bitwise ANDed with Hamming index minus 1. Let's make sure that's in parentheses. I think minus has higher precedence. But so if we bitwise AND those together, that should be fine. And that is 0. Then we know it's a power of 2. So we want to do the opposite of that, which is, well, it's not equal to 0, then it's not a power of 2. No. We do want to go with power of 2. Yeah. Then we make the Hamming index bigger. I think that sounds correct. So while a power of 2, which is where a check bit would go, skip. Okay. So I think that sounds right, and thank you again for that. That sounds like a pretty good solution. And then, well, power of 2. Okay, so now we know the Hamming index is the first available index to fit stuff into. Okay, so that should be easy enough. Then we just do Hamming code sub Hamming index equals value sub I, but value's not an array. So we need to figure out what the bit is for value, and we can do that by doing value mod 2. So get the last bit at the end of the value bit string. Okay, and then we can do value. You can either shift it 1 bit, or I'll just do divide equals 2. Shift 1 bit to the right. Hopefully that's not too complicated. But I think this is a, yeah, that seems like a really good solution. This is a pretty efficient way to just copy it over. Alternatively, like somebody else said in the chat, you could always just say, could basically just do these two operations over and over again. If this just seems kind of complicated, which is fair. You could say like Hamming code sub 2 equals value mod. Why is that going? Value mod 2 value divide equals 2. Hamming code 3 4 equals value mod 2 value divide equals 2. You can do this as well, and then just keep going for all of the other ones. I kind of advise against this in practice, just because this is more general and it will work no matter. We could change this 12 here, and these to be variables. We could make it work with any bit value of, or like bit length of string, if we did it that way. So also an option. So an option. I'm going to comment it out though. So whichever you think is easier, I'm going to try to keep it as generic as possible. So now we've copied over all of the data values, or the data bits, to the thing. Now we just need to calculate all the check bits. Okay. So this one should be a lot easier. And I equals 0. I less than 16. 8? No. I'll just say 9, I guess. I'm just going to say 16. I times equals, and I know I made a mistake here. I equals 1. Check bits. Okay. So for this one, we're going to want to calculate. I guess I already commented that. Calculate the check bit. So I will be the index of the check bit. So hopefully it's clear that all of those are powers of 2, and the first one is 1. So I'm going to start at 1, and then I'm going to times it by 2. So the next check bit would be 2, and then I'm going to times that by 2, and I get 4. And so that's going to generate all the powers of 2 for however long this is. So again, I'm just going to stop at 16, because we know that the last check bit for a 12-bit string is 8, but whatever this would be the either 1 higher or some number bigger than whatever your highest check bit is. I'm just going to say 16. But smaller than whatever the next power is or equal to. Okay. So, for calculating the check bits, we probably want a second for loop, right? We want to go through the actual Hamming code array and find the positions of the what's it called? Of all the matching data bits, and then calculate the XOR, right? So I think what we'll do is we'll say bool check bit. So we'll just keep a temporary check bit to calculate it, and then we'll just store it at the very end. So temp check bit equals false. So we'll start with the check bit equal to 0, because if I have no ones whatsoever, then the check bit should be 0. Because 0, 1s is an even parity, and if you remember, even parity is 0 and odd parity is 1. So we'll go with the false there. So next we will go through each of the values. So this one I think is a lot easier, or at least it should be. We'll go through starting from that index and then in blocks of the value. So in this case, we know that we're going to go in terms of I. In fact, we probably need 3 loops for this, which is not great, but we'll deal. So int j equals 0. No, I'm sorry. We want to start at I, and we want to go that many bits. So int j equals I, while j is less than the bit string j++, and then we'll say for int k equals j. Maybe this is a little bit more complicated than I thought it was. K less than I. Just make sure that all of this is correct. K++. So I want to first start counting at that one. Well, I want to go one past it. I don't count the actual check bit, right? So let's get past that. Manual, yeah, that's fair. This is a little abstract, but I am pretty sure this works. I guess at least the point I want you to take away from this is to just use a 12 Boolean array, because I think it's easier. I'm not actually explaining any of my thought processes here with this very well. And I'm not even sure it works because I'm not going to have time to compile it. But, you know, I always suggest writing things ambiguously. Yeah, so long as it works. For the sake of this program, if you just allocate a 12-bit array and then just copy it all over and just do this, that's fine. And then manually calculate all of those data bit, like, linear equation, that's okay, I guess. As long as you generate something. I might not even finish this just to talk about the rest of the stuff. But this is the general setup. So this is data bit to start counting on for block. And then this is how many data bits we've counted. There's going to be one problem with this, and I just need to so if k equals I plus 1, if this is the check bit block, that doesn't work for the 1 though. No, I don't want to do this. I want to do that. Let's not move one over for the check bit. Let's skip it manually. If this is the check bit itself, shift 1. And then we k plus plus. Oh, sorry, did somebody say something? And then, okay, I'm only going to write like 2 more lines of code, and I think this is fine. And again, I'm not even sure that this is all works, but temp check bit XOR equals, what do I even call it? Hamming code sub k. And then the last thing we do is we say that Hamming code, I might even have to subtract by 1, because this is a 1 to 16. K equals I j. Yeah, I need to subtract 1 on the indices because that starts counting at 1. So I say Hamming code I minus 1 equals temp check bit, and then just write this a second time for calculating the other one. I think this all works. This is a way to do it for like any arbitrary Hamming code length. But if you want to do this and just assign them all and then use the linear equation with the XORs that we came up with last time, go for it. I won't blame you. Let's at least discuss what the rest of the program does, so I don't just waste time writing all this stuff again. So, yeah, what we should be doing, we should generate the Hamming code from the CPU. So this will generate the 12-bit Hamming code that has the 8 bits embedded in with the 4 data bits at positions 1, 2, 4, and 8, assuming that we start counting at 1 and not 0. And then what we want to do is we want to corrupt it. So corrupt the Hamming code. So you can corrupt, it's up to you. You can either try to corrupt 1 bit of the Hamming code, or you can corrupt every individual bit if you want to do the double error detection. Up to you. Just write a function. It's in the syllabus again, or the rubric. Write a function that corrupts these bits and has some % chance, like 10% chance, to corrupt everything. Then what we want to do is we want to check if the data has any problems. So we will calculate something. So we'll say bool comparison Hamming 12. Can we just add or subtract the number from the Hamming code to corrupt it? Yes, although if you're doing it as a Boolean array, you can just not it. If you do it as an integer array, yeah, I guess you'd have to do that. Oh yeah, you did it in Python, so no, that should still be fine. You'd have to do all of these as Booleans anyways. Yeah, I would just say keep it as a Boolean list if you're doing Python, or array if you're doing it in C++, and then just not the value if you happen to corrupt it. You could do an integer array where each one is either 0 or 1, and then you kind of have to do like modulus 2 arithmetic. But I think if we just limit it to Booleans, it's fine, and easier for the sake of doing XOR operations. So correct Hamming code. We corrupt some amount of bits, and then we want to check it. So this should be the comparison. No, I'm sorry, corrupt it. So we want to compare it. So I'm going to want to generate the comparison Hamming from the generate. It doesn't even show up. That's unfortunate. Hamming code from code, I probably said. From received code. So we'll take whatever Hamming code we received, corrupted or not, and we'll generate the check bits for that one, and we'll store it in a copy. That way we can XOR it. For the double detection, single detection, we also have to add the parity bits for checking in the received end. Yep. So, yeah, in that case, you'll need to do a 13, and then calculate at the end. So if I was to look at my pseudocode, or no, this is the pseudocode, C++ code here, generate parity bit, and then maybe we would just throw that in at the end here. So we say 13. If you want to do double error detection, in which case you could just go through and calculate Hamming code sub 13 equals, and then just XOR through everything else. So that was actually pretty straightforward. Definitely do that one with a loop. I don't think you need to hard code that one. Just go for int I equals 0 to 12 XOR of 0 through 1 through 12, 0 through 11 in indices. Right, yeah, so just generate the parity bit. That one's pretty straightforward, I hope. Just it's the XOR of all the other bits. And you've already calculated it up to this point, so yeah, this is going to be on video as well. Yeah, don't worry too much about understanding this code. I didn't explain it well at all. I just kind of threw it in there. But understand, and if anything, look at last week's discussion. You want to understand, how do we calculate a Hamming code? And then this code right here, I think, is very important. We're going to do basically the opposite for load IO. Really, pretty almost just the same code, but the final storage is backwards. Yeah, so I think let's just, and again, if you have to go because it is 12:50, feel free to go. But let's just at least walk through this, because this is the meat of your actual Hamming code thing. You should generate the Hamming code for wherever the sender is. So for this one, it's the accumulator. If I'm doing it the other way around, it's going to be the IO device. I want to corrupt it then. If it's going to have a corruption, it could totally be fine. You want this function here to corrupt some random amount of bits. And then you want to generate the Hamming code on the receiver side. So you want to take the original Hamming code and only change the check bits. So basically only do either this for loop, or if you're doing the individual indices, then you do 2 for whatever. Keep going until you hit all the not check bits. Write out the linear equation, generate the check bits again. And then after that, the next step should be pretty easy. So we will make one more. So again, I probably want this to be 13. If anything, I'm not sure if you have to allocate space in advance to generate the syndrome, which is just the XOR of these two, right? So, assuming you have some sort of thing, we say the syndrome is equal to XOR of Hamming and comparison Hamming. So we take the XOR of those. The 13th bit will be the parity bit, and everything else will be the bit string. So, yeah, at that point we just need to check the syndrome. So if the parity bit... Oh, yeah, and the order of this was important. Somebody was telling me about this. We need to do it before we calculate the check bits. Yeah, so I'm sorry. Calculate syndrome for all but the parity bit. I think we need to calculate it before we calculate the actual correct check bits. So, we could even have just a Boolean, whatever. My code is kind of sloppy. But we would say the parity equals calculate parity. Actually, this should be easy enough. Hamming 13 XOR Hamming comparison sub 13. So, sub 12, because it's off by 1. So we need to look at the parity bit that we stored originally. And again, you could store this as an individual Boolean. My implementation is kind of just trying to get it done in half an hour. I'm sure you have more time. So we want to compare the parity bit and just make sure, I wasn't very clear on this in the Discord, that you calculate it before doing the updated check bits. You compare the immediately received Hamming code string with the parity bit from the original. Wait a minute. I don't have the original. I'd have to calculate that right now. Calculate. No, I'd have to do a function call. Calculate parity bit of Hamming. Yeah, so I'd have to calculate what the parity bit should be, XOR it with the one that I received, and then we'll do some checking with that. So check the syndrome and the parity bit. I guess in the interest of time, I won't go into a whole lot of detail, but I did put a table in the Discord chat if you want to look at it. I can post it again. Basically, if the parity bit is a 1, then we know that there was a problem. Potentially, either the parity bit itself was corrupted, or sorry, not the parity bit, but the XOR of the parity bit. We know it. If the XOR is 1, then that means that the parity bit of the original does not match what it should be now. That either means that we have a corruption in our data, which is affecting the parity bit, meaning that there is a flip in one or more of them. That would be an odd number that caused the parity bit to be wrong, because the parity bit would be off, right, if there's a odd amount of data corruptions. Or it means that there was no corruptions and the parity bit itself got corrupted, or it means that there was an even number of corruptions, hence the double error detection, and that the parity bit is also corrupt. In that case, we just really have no idea. It's hard to tell. So, check that table. I'll post it again, I guess. You want to check the syndrome. Check if there are any errors in it altogether. If the syndrome is 0, then you're probably fine. In fact, I don't think it's possible to have a zero syndrome, like entirely nothing in the syndrome, if there wasn't a corruption. Right? No, that's wrong. I guess it's possible that you just have it at even intervals. Yeah. Let's have an account for resetting the data in the case of a double error. You can, so that's up to you. So, assuming at this point you can So I guess just let me put my last line of thing here. If you just want to make it easy, just say IO device equals AC, CPU.AC. That's fine. Either that or you take the Hamming code and decode it and you try to correct it. So if there's an error, you can correct it. If you get a double error detection, you can maybe throw this all in a while loop. So while double error, and then say Boolean double error equals true, and then keep doing all of this stuff. If you wanted to check for double error, you can mark when you don't have a double error. So if you get no double error, you can set it to be false, and then you're done and break out of the loop, and then keep sending it over and over again. If you get a single error, you can potentially do the correction if you want to, and then take that data and then decipher it back from all of this garbage that I wrote back into an actual integer, and then store it into the AC. I'm not going to check for super authenticity, but if you wanted to do it that way, which is how it actually does it, then be my guest. You could just do this, that'd be fine. I'm not going to be super picky about that. But at least I want you to at least identify them. I would kind of like it if you would do the error detection. I guess I'm not expecting you to fully like parse it back into an integer. But I at least like you to maybe print something out if you're not going to do that, just so I know that you knew what you were doing to begin with. And then just last thing, I guess, the code for load IO is just the same, except we generate the Hamming code from the IO device because that's where we're sending it from, and then we do this backwards because we're storing the IO device into the AC. Oh, and then Jorge just posted the assignment 3, it looks like. So that's going to be fun. 1,000 points. Oh boy. Alright, so I think that's probably fine. I might have made it look a lot more overwhelming than it actually is. Don't be afraid. I know I wrote all this stuff. Don't be afraid to just do assignments and just come up with a linear equation for the time being with the XORs. That's okay. But any other questions, I guess? I think that's everything. Oh, Mantisa, are there going to be floating point things? That'd be fun. Actually, that makes sense, considering you guys are doing data representation.
Hi. Does anybody have questions about the assignment, phase 3? I can give you a very quick overview. All you have to do is implement floating point as a new data type that you can store in your machine, and then appropriate load and store, and at least an addition and multiplication of it. And in terms of the points, we're grading everything together at the end. So what it means is that the majority of the points come from the thing working at the end rather than the phases being partially done. So you will need floating point. You will need a way of basically creating a floating point value and then interpreting one, which means you would have to separate and convert your significand and your exponent and all of those things back into a normal float. You can create unique ones. That way you can make your life easier for the arithmetic opcodes. That way you don't, otherwise you won't know if you're loading in a float or you're loading in an integer. So you have to create specific opcodes, which should be the exact same as you did the other ones. And then to make life easier, create a different accumulator that only works for floats, and then that you can create as a little float variable. And the number of points don't matter at the end of the day, because what matters is the percentage of the grade of the class. I think this is worth 20%. So that's just simply as a scale in comparison to the other parts. So I just thought I'd post that so you guys are aware of it before the weekend. But that's it. Anyways, I'll let Sam take over again. Thanks.
For sure. Thank you. I think that was everything, anyways. I guess yeah. Last thing I'll mention is I'll probably just throw in. I'll update that resources file with some more opcode, and then write a program that does floating point, so that you guys have it. Alright, I guess on that note, unless anybody has any more questions, I guess I'm probably going to close out the meeting. And again, make sure you post in the chat if you didn't already for attendance.